Hello, today we're going to discuss HyperAnalyze, product offered by Agralogics to quantify, measure, monitor, and analyze a field, an agriculture field, anywhere in the world, specifically designed for California initially, but really available anywhere in the world. The motivation behind this product was really driven by the advent of a lot of public data that is available, and we got a lot of requests from our customers wanting us to compile all that information for a given field and offer that as both an operational and a transactional report to help them manage their agricultural transaction or operation with more efficiency and with more data. Based on that market feedback, we analyzed and have spent about the last 1 year in putting together our first beta launch of our product, which we're calling HyperAnalyze. You can think of HyperAnalyze as a top of funnel due diligence report for a agriculture transaction or land transaction that you wish to do. And a lot of people, they consider a bunch of different fields and ranches, and not all of them are ones that they're going to actually buy, but they would like some background information about them to help them essentially narrow it down to a subset which they can do a deeper diligence on. HyperAnalyze is meant to provide that early top of funnel diligence information for land transactions, and that's the main primary mode it is designed to do. It is also useful for nitrogen management and irrigation management and water budgeting for a given agricultural field. And so we also recommend HyperAnalyze for operators who are looking to analyze their field and adjust their nutrient and irrigation planning for the subsequent year. With that, let's launch into it. So as the word HyperAnalyze suggests, this is an analysis. There are multiple analyses that have been compiled of a given field, and all we get from the customer for this is their boundary of their field, and often it's just their parcel number. And once we have the boundary of the field in a KML, KMZ, or shapefile, or a parcel number, Agralogics servers then compile this report. It usually takes between 24 to 72 hours for us to compile this. It's a huge amount of data going back 5 to 10 years. And then we compile this information and provide it to the client. And the way we provide it is through a URL. And in this recording, I'm going to walk you through what the analysis is, what that sample report looks like, and what that URL that we give the client looks like. And it's all hosted by Agralogics servers. So here we go. Before we get started, a quick reference. This is a georeference that I'm going to go through of what the report looks like in order. So we're going to look at the map of that field. Then we're going to go through its soil properties based on soil grids data. We're going to look at its groundwater trends. We're going to look at its what we call hyper yield, which is essentially its yield map based on evapotranspiration for an entire previous year. We're also going to look at how that yield breaks up into different performance bars and quantify that in terms of acre performance for specific parts of the field. We're then going to look at 5-year trends for both water demand or evapotranspiration and uniformity, followed by the monthly budget, both a 2-year and a 5-year average for the field, which is the evapotranspiration budget. And then look at chill portions and chill hours, which may be useful to predict yield for things like pistachios in California. Look at wind speed, which is very useful if you're looking at field because it informs many different things, things like pollination, etc., but also your crop protection, cultural practices, and then last but not least, the precipitation, both the 2-year and 5-year average. So with that, we'll jump right in. So the report begins with essentially a map of the entire field. This is what the client typically gives us. This is a field in California, and the client generally gives us a boundary file, which is in KML or KMZ format. Sometimes the client can also give us a parcel number, and we can get the outline boundary of the file of the field from the local assessor's office. So with that, and that's the only piece of information the client gives us, we put that information into Agralogics servers, and the report is cranked out. And this report is quantified or addressed by a URL, which essentially is what we provide the client at the end of the report within 24 to 72 hours. So there's once you open the URL, the report looks just like this, and what you see at the end of the report is essentially this is a zoomable field, so you can zoom in and zoom out, and if you go down, so here's just zooming in, zooming out, and you can move the field around, but there's a scroll bar at the end, and that allows you to scroll down to see other parts of the report. So the first is just a map, nothing magical here. Now we get into the soil properties. The first of the soil properties is a soil map for the pH. This information is gotten from Soil Grids, which is an international global database of soil properties measured by international agencies like the NRCS and USDA, but also other international agencies participating in. Several properties of soil are quantified in these raw properties, as well as derived properties is what we're going to walk through. So as this shows, the pH of the soil has a slight non-uniformity, about a little more like 0.5%, 1%, not much, but a little bit towards the northeast corner of the field. It's about 8.4 here, and then down below it's 8. What's really interesting is as you move your cursor on this report, it tells you what the lat long, the X is the longitude, the Y is the latitude, and the Z is the actual value of what that pH is. And this is at the depth of 60 to 100 centimeters, which is roughly 3 feet. So this is the root zone of the plant for permanent crops. And we have other root zones, other depths as well, from 12 inches all the way down to 2 feet. So this is customizable for different depths, but typically people want to see a 3-foot depth. And these soil properties, again, come from an international database maintained by reputable organizations like the NRCS. And you can zoom in to a particular area and see what that looks like over there. So it automatically redraws, and double click, and it comes out into the main. You can zoom out and zoom in from here. I believe if you double click, it'll come back in. There you go. So that's what the pH looks like. This looks a little acidic, so might have a need for balancing the pH out in the topsoil and doing some soil amendment. This is the natural way the soil is in this area for this field, and field to field there could be changes in soil. So for example, another report that we have here, we can actually see that another report we have here, we can actually see that the pH is actually different. So here it's between 8 to 8.1, much more uniform. That was still 8.4, and even though this looks a little funky in terms of its non-uniformity, the actual values, which are on the y-axis, which you see here on the color chart, show that it's much more uniform. So anyway, moving on, that's the pH. Going into sand percentage, this is the percentage of sand that's in the soil. This soil is showing about 47% sand. This is at the root zone depth. Another field for comparison is showing actually something along the lines of 33% sand. So this field has a lot higher sandy soils than, for example, this field does. And again, the sand varies by about 5% across the field. So there's a little bit more sand in the southeast section of this field than the other field. which looks more uniform, but essentially, the sand percentages are mentioned here. Again, this is raw soil properties that come from national databases maintained by the government. This is silt percent. Remember, soil percent here was 47%. Silt percent is 35%, pretty close, 35 to 36, 37%, very uniform. And then clay percentage, low clay here, high clay over here, going from between 16 to 17.5. And so you can see this is a pretty well drained, sandy soil. Almost half the soil is sandy. You compare that with this field, which is, sand is about 33%, silt is about 36%, and clay is about 30%. So this is much more balanced soil-wise than this field. Then you have bulk density, which is measured by grams per cubic centimeter in terms of water. So the ability for water to be held inside the soil. So you look at this, because it's pretty sandy, it's got fairly low bulk density. Again, comparing it to a different field, you can see that the bulk density here is a little bit higher. Actually, it's about the same. And again, bulk density is a function of all the different parameters and not just of sand and clay and silt. Moving down, you see KSAT. Now this is starting to go into derived metrics. So here, we're now over here in KSAT. KSAT is essentially the, layman's word, it's the infiltration rate. The technical term is the hydraulic, saturated hydraulic conductivity. Essentially, it's the conductivity of water when the soil is saturated. So this is a derived model that takes bulk density, sand, soil, silt, and clay into account and computes that based on public models to what it is for different parts of the field in terms of inches per hour. So this is the vertical movement of water at saturation that this soil will allow. Anything above that will flood the soil. So essentially, this is the pitot transfer function for the soil that takes the water to a certain depth, and this is 0.059 or almost 0.06, and over an hour. So in a 24-hour period, you're looking at slightly over 1.2, 1.3 inches for the day. Fairly well-drained soil over here. As a comparison here, this soil had a little bit lower sand percentage, so its KSAT is actually slightly lower. It's 0.05 compared to 0.06, and so this one would be 1.2, 1.3 inches. This one would be 1.1 inches or so per day. So that's what KSAT looks like. Moving down, again, lots of information to cover. This is the cation exchange capacity. So cation exchange capacity is a measure of how willingly the soil gives up its cations, which are the nutrients in the soil, to the roots. And so cation exchange capacity tells sort of per kilogram of soil how many moles that particular soil is willing to give up in terms of cations. It's a measure of nutrient transport efficiency. So here you see CEC of about 14.8, 14.9, going from 13. So fairly low CEC over here, going to fairly high CEC at this point. So in terms of nutrient management, this could be useful in terms of actually providing nutrition for the soils. Whereas if you look at the CEC over here, you see numbers in the 24 down to 20 over here compared to 14 and 13. So quite a big difference between the two soils and two fields, and that's the whole purpose of this report, is to be able to provide that field bespoke information. Moving on, this is the available water capacity. So the available water capacity is the amount of water available to the soil, maximum amount of water in percentage that is available to the soil if excuse me, the soil was saturated. So essentially it's about 17-18%. You can see that in the south east corner you have a little bit lower water holding capacity. In the northwest it's a little bit higher. Roughly I'd say about a little less than 10% difference, but fairly uniform. Compare that to the other field, and you have available water capacity that's roughly 33%. So this soil will provide a lot more water to the soil than this does, and again that has to do with its soil composition. Remember, this field that you're looking at right now was actually a more sand, so it makes sense that its available water capacity would be lower. That makes a big difference in terms of how you want to irrigate this field, because the rate of watering or the irrigation for this field will have to be much more frequent and smaller amounts, whereas the rate of irrigation for this field should be relatively to the previous one a lot higher and more infrequent. And so essentially the two irrigation regimes can be informed by this available water capacity, and this information is really quite useful for irrigation companies and your irrigation consultant, who is going to use this to dial in the irrigation emitter rates for your fields. So quite useful information, we think. Now we come to the next section, which is groundwater. So as many people know, California is always stressed for water. There's a long-term drought that's going on in the western 1/3 of the United States, sort of west of the Colorado River. And some years it's much better. We get good rain, good snowpack. And other years it's drought and not as good. This year we have about 60% or so of our snowpack and precipitation. So a little better than really bad, but not quite at normal. We're going to move on to that. And what we do here is we look at all the public groundwater wells in the groundwater zone or hydrological zone that this field is in. And so different fields will be in different hydrological zones, and the public wells in those zones, the ones that the government is using to monitor, these are wells set up by the USGS and measured by the Department of Water Resources. We take that data and we essentially interpolate that both in time and space for the last 10 years. So we take 10 years of data, and the blue line is the best estimate of all the wells around this field, up to 10 wells around this field, weighted average in terms of distance from the field. But then also we look at their data in terms of their depth. And here you see the well depth actually goes up a little bit. This is depth to water, so from the top of the well to water. And here, the well depth drops precipitously from 2016, 2015 onwards. And this is where the drought started to hit real hard for this field. As you can see here, this is actually a slightly different area. And here, the depth of groundwater is much deeper, so it's 300 feet. And it's been stressing all throughout the early part of the decade. And then in 2015 onwards, it starts to get better. 2016 onwards, it starts to get better. And same here, this is actually getting worse in 2016 all the way to 2019. So it's a very different profile of what the groundwater is doing. And remember, this is all the public data, and so we're just basically making a best mathematical estimate of what the groundwater depth is based on nearby public wells. But it's very useful information. Then we fit a straight line to it, and we just sort of quantify that. We estimate the depth of the groundwater to be about 120 feet or so, and it's declining at the rate of about 10 feet or so per year. Whereas here, it's more or less flat, and you can see a slight increase, so it's actually getting better in the more recent years. And if you fit a line here, maybe it'll show you something different. But you have the benefit of both the raw data and the best estimate, mathematical, statistical estimate of what that depth looks like. So moving on from there, we think this is very useful if you're doing a transaction, for example, and what your well depth is. This is a very interesting next phase. So this is what we call hyper yield. So here we're taking a whole year of evapotranspiration data, the actual vigor of your field, and we're layering it like pancakes, one on top of the other, and then of course looking at it from the top down. And what we see, we then normalize that by the average. So we look at every piece that's higher or lower than average, and we put it in 1, 2, 3, 4, 5, 6 different bins and different colors. So anything above 20% of average vigor is in the dark green. Anything below negative 20% of average, we put in the dark red bin, and then the colors are in between. And so what you see here is a contour plot. What this shows you is what part of your field is really doing better than other parts, and this can be used for differentially creating a foliar spray or other types of soil amendments if this is a soil issue. But it shows you where the non-uniformities are. It shows you areas that are more stressed, and in fact you can zoom in and go to those areas if you actually put the lat long. So the x is the long and y is the lat. If you put 36.32389 comma negative 119.6968 into Google Maps, it will actually take you to this location, and you can see what's going on here. Is there a problem? Is there a pest issue? What happened here? Because clearly something happened. This is data that is satellite derived from multiple weeks. We take satellite photos every 5 days for the whole year, and use that to essentially inform the field. And that's what gives us this mosaic, which we call hyper yield. And the reason we call that is because this is a proxy of your yield. This is where your yield is getting negatively affected, and this is where it's contributing really well. So you want more of the greens and less of the reds. We further break this up into a bar chart that shows the performance by number of acres. So this is less than 20%, less than, between 10 and 20% less. And so these two bars are the underperforming ones. These are sort of average, and then these two are doing really well. And then we put these, if you mouse over it, you can actually see how many acres are in each. So this has 6.72 acres. This has 1.08 acres in that particular color. And then, you can go down here and see what that looks like in terms of the overall pie chart. Generally speaking, double-digit underperforming areas, where it's 13, 14, 15% is considered not that great. Where we've seen fields that are really good performing in the single digits. In fact, let's look at this field here. This is double-digit as well. Let's look at here, another field over here. And I think this is also double-digit, but essentially, fields that are single digits are usually pretty good. When a field goes into double digit, there's definitely room for improvement. So there's room for improvement bringing this bar down. There's always going to be 5, 6 bars because we're dividing by the average. There's always going to be different colors, but the goal here is not to pass judgment. It's to identify opportunity and areas where the opportunity is for you to improve things. So certainly something's going on here, something going on here and here, and that alone could reduce that quite a bit. So then moving on, we start looking at the evapotranspiration trend, and this is a very interesting trend. So this shows big spike in ET, and then a small ET growing, and really growing. And what this is showing is that this is a growing orchard. So when you're looking at an orchard, this was a cornfield, and you can see there was a cut here, and then growth here, and then finished at the end of the season. And mousing over this, you can actually see the dates. This is the amount of water, and it's a proxy for how much your fields are growing. The evapotranspiration tells you the overall crop health for the field, and you can see that the crop is growing here, and so you can see that this is in 4th leaf for almonds. Contrasting it with another field here, This actually shows that there's slight growth here, a couple of really good here, something not that good happened over here. So opportunity for people to find out what's going on. So this gives you a diagnostic and essentially also a time travel back in time to see what happened on this field, almost like a Carfax, where you can see the history of the field, of what actually happened on this field with last 5 years of data. Same thing with the uniformity. The uniformity of this fields, both these fields is actually pretty good. This is in the 94% range, just a few outliers. I would say that's pretty good. Same over here. The uniformity here looks quite good. There's a few outliers over here and here, but mostly it's in the 95%. This field definitely looks more uniform. And then here's the water budget. So this is a growing field. Remember, we were seeing this growth over here. So the water budget in this time frame, which is the last 2-year average, would be a lot, higher than the average of the last 5. And so that's what this shows. Month by month, it shows what the water budget is. In January, 1 inch. February 2.1, 1.47. This is 0.76. Sorry, this is 1.47. This is 2.68, etc. And you can see the bars are bigger in the last 2 years than in the last 5 years, month by month. So that gives you an overall water budget, and the title actually tells you the total budget for the year is 42.65 inches, or in volumetric units, it's 207.71 acre feet as the average of the last 2 years. So, when you're looking at this field, you know that it's taking about 42 inches of water. If you look at another field, for example, here the water budget is a little bit higher, it's 48 inches. So, field to field water budgets can vary, and those are very useful because, every inch of water is precious in California, and the last bit of water is the most expensive. And so if you know what the exact budget is, you can save yourself a lot of cost in terms of water in some stressed areas. So again, knowing what the water budget is quite useful. Going into chill portions, this is an accumulation model that ANR put out, University of California Agriculture and Natural Resources, and we simply compute that. This computes the amount of chill hours. This year was quite low. It's not quite done yet. The chill is growing, but we had less chill this year than the previous 4 years. This is chill portions using what's called the dynamic accumulation model. These are actually 4 different models for chill hours for the last 4 years. So this is the 32 to 45 degrees Fahrenheit model. So it accumulates hours that are between 32 and 45 Fahrenheit. This is just accumulation of hours under 45. This is a model called the Texas A&M model, which decrements certain portions, and the Utah model. So again, different people use different models. It shows the chill hours actually going up last few years for most of the models, except for this, it has going down a little bit in a few years ago. But essentially, you see quite a bit of consistency in that. Next, we have wind speed. This actually shows the wind, not just the average speed, but what the distribution for a given month looks like over the years. So this is statistically the minimum, the median, the first and the third quartile, which is the 25th and 75th quartile, and then of course the upper and lower fence and the maximum and minimum. And it essentially shows the distribution of what the wind looks like. Typically, you'll see winds between 2 and 3 miles per hour in the April, May, June timeframe, which tends to be a little bit higher. This area is a little bit higher in wind. If you contrast that with this field, for example, you see, actually this is about the same as well. So these fields are probably close to each other in wind speed. Yeah, that's very close. Then you have the precipitation. This field has about 8.6 inches of precipitation, and mostly happens, and this is both the 2-year and 5-year average. So if you see the 5-year average, used to get a lot more rain in January, February, March. The last 2 years we've been gotten more in March and then some in April. A slightly different change in terms of the actual precipitation. And this water is really useful and important because it contributes towards your water budget for the field. So that's essentially the HyperAnalyze report. We hope that this provides asset managers and growers and transaction buyers and sellers of agricultural land with the appropriate data-driven information analyzed enough to provide some context and meaning and ability to take some action, but while keeping it general enough so that if you want to consult with your agronomist or your soil scientist or your crop advisor, you can take this information and essentially get expert advice. So with that, we will conclude our description.